Okay. Well, welcome to, ooh, that just sounds loud to me. Yeah, I'll move it down a little bit. I have a loud voice. Welcome to this afternoon session where we'll be focusing on manufacturing processes, and of course, always materials being very important in that because that's what we're working with. I'm the moderator. I'll give a first sort of an overview, introduction, and then we have three speakers following me. Dr. Justin Morrow, who's a postdoc at UW-Madison, Assistant Professor Sang-Hee Min, also from UW-Madison, and anchoring the team is Chris Smith from Wolf Robotics. So I thought I would, you see here my affiliations and who I am. I've been at the university for 13 years, but last year I spent 12 months serving in the Advanced Manufacturing National Program Office. So I thought I'd give sort of a very high-level view of what I've learned is happening in the manufacturing sector there. And just so very briefly, this Advanced Manufacturing National Program Office is part of an interagency team across the federal government to try to foster, help move manufacturing forward in the United States. It is, while it's an interagency office, meaning we talk to people in all different kinds of agencies in there, it's housed at the National Institute of Standards and Technology in Gaithersburg, which is part of the Department of Commerce. And I think one thing that I really learned, which is encouraging to me, is that there's definitely an appreciation in Washington of the impact that manufacturing has on the country, certainly under this administration, but across the board. So manufacturing is a nonpartisan issue. Everybody agrees it's important. Where discussions and arguments still happen is what should be funded and how to appropriate funds to foster different things. But they see the importance to the U.S., particularly on the innovation ecosystem. All right? So this is very encouraging. And I think because of that, spread across the government, there are a number of national initiatives out there, many of which I didn't know about until I worked there. The top one, the Hollings Manufacturing Extension Partnership, has been around for almost 30 years or more than 30 years. And it has, as you'll see in this slide here, there are 50, well, in all 50 states and Puerto Rico are centers, manufacturing extension partnership centers. We have two in the state of Wisconsin, one housed here in Madison, one in Stout, at UW-Stout. And they work really at the highest technology readiness level with companies in assisting them in better use of manufacturing technology or adopting new ones. Three newer initiatives over the last couple years are the National Network for Manufacturing Innovation, which is the main sort of initiative that the office I worked in was working on, is still working on. I'll talk a little bit more about that. Also, NSF and NIST co-funded the startup of what's called M-Foresight, Alliance for Manufacturing Foresight, a 3-year cooperative agreement to try to start a think tank, essentially. They call themselves a think and do tank, but okay. To be the voice for manufacturing in the United States. That's just still in its first year. And the other thing that's very new, and I guess this should have been gray too, is that manufacturing universities legislation, which Tammy Baldwin has been espousing and promoting for a while, but is probably going to happen now because this year they put it into the Defense Reauthorization Act as a piece of that. And so the likelihood of it being funded is high. And that means that likely in 2017, maybe the second half, we don't know, there'll probably be a solicitation for universities that want to improve their existing manufacturing engineering programs or create new ones. And it'll be funded by the Department of Defense. So I think certainly in Madison, but other regional universities we're in a very good position to go after that because we already have a strong sort of manufacturing base, but maybe formalize it. Here in Madison, we have a master's degree in manufacturing systems engineering. We have an undergraduate certificate, that's like a minor. We don't call them minors anymore. We have an undergraduate certificate in manufacturing engineering that was just launched last year, but we don't have a degree specifically in that field. So I wanted to just say a few more words about the National Network for Manufacturing Innovation, because I think it highlights sort of at least what the industry participants in this, which are many, over 800 members in these 8 institutes already, and the federal government see as important topics in manufacturing. And these are translational or applied R&D centers. The goal of these manufacturing institutes is to take maybe what at a university we might get to, and if you're familiar with technology readiness levels, that might be 3. If we're really good, push it up to 3, maybe 4. Take that across levels to the point where industry can actually apply that technology. And oh, sorry, that's a little animation there. So here are the topics. On the previous slide on the map, you saw the names. The topics that these 8, the 9th one down here was announced, but they're still negotiating the contract, so that's why it's in a special category at the moment, that these are focused on. And here are another 6 that are currently under solicitation. So these will be launching, if you will, starting up next year. So there'll be 15 manufacturing innovation institutes across the country, certainly by the end of next year. It's hard to set a deadline. So again, you see sort of where all of these, by the way, all of these topics that have a name already associated with them, up through 13, were identified through a rigorous process by the Department of Energy or the Department of Defense as being important to their mission, along with consulting the private sector. These last 2 don't have a topic listed because the Department of Commerce is running an open topic solicitation. Final proposals are in, they're being reviewed, but I don't even know what the topics are that the teams proposed. So they didn't say, we want proposals on a special topics. You tell us what's important to US manufacturing and where we need an institute. So when these get announced, we'll learn what those topics are. All right, so I just thought this might be interesting to see sort of where emphasis and money's going. Each of these institutes is being seeded by the federal government with $70 to $100 million and at least a 1-to-1 cost share, meaning the rest of the money comes from the public sector, right? And that can be companies, universities.
Tied into the manufacturing universities?
No. Not to my knowledge. Now, if it eventually gets tied in somehow, that could be, but I think they're separate things at the moment. Yep. So maybe we can get one in Wisconsin at some point. We'll see. There's one in Chicago. That's the closest, the Digital Manufacturing and Design Innovation Institute. All right. So then I want to give a brief overview of what's happening in manufacturing process research, which is primarily done in the Department of Mechanical Engineering. We've got a lot of manufacturing systems research done in industrial and systems engineering. And sorry, I should also say there's very good manufacturing process research done in material science and engineering. So we have 8 faculty members in mechanical engineering focused on manufacturing problems, research and teaching. And I've tried to sort of organize them into these headings. Actually, in our parallel session, Tim Oswald and Natalie Rudolph are speaking about polymer manufacturing. In this session, you're hearing me, and then Sang-Ki Min will also talk, and then we have a faculty member in digital manufacturing, plus numerous others that are doing projects in manufacturing, but don't yet sort of have both feet necessarily in that area. And I'm just going to give some highlights of some of the projects I work on, except for laser polishing, which Justin Morrow will talk about after me. So one area is friction stir welding. So a solid state joining process that's being used extensively in making structures for transportation systems, be it ships, trains, tractor trailers, these kinds of things. It's commercially used primarily in aluminum alloys at the moment, though it's been proven to work in steels, titanium, and so on. The economics of that are a little trickier because of the tooling that's required to survive the temperatures. In my lab, I'm a mechanical engineer, and I collaborate with mechanical engineers with controls expertise. We've been approaching friction stir welding from that, and one of our achievements is being able to both measure the temperature at the interface between the tool and the weld zone and control it. And so I think that without going through all the details, sort of the figure I like the most is this one right here. The blue line shows the measured temperature. The red dotted line shows a control setting. So we said control it at about 563 here, then drop to 550, and it sort of followed that with some wiggle around it. And so it can follow our control commands to maintain a weld temperature that we want. We've also worked on force control. Believe it or not, that's important in friction stir welding because of the very large forces involved. This is being done by, this experiment being done on a CNC milling machine, though large industrial robots can do it as well. And actually, friction stir welding with an industrial robot is something that Chris Smith, our last speaker, first introduced to the world, working with Friction Stirlink in, Waukesha then and Brookfield. We've also recently come up with a method of taking the force signals that we can measure during this process, the transient force signals, and use them to figure out if we are creating or leaving behind a void, a cavity, inside the weld that we can't see. Right? So as a method that could be applied in real time for defect detection. And essentially what we're doing, there's a lot of details here, but we're looking at the transients in the force data. And so in this case, we're looking at the third harmonic over the first harmonic for a particular tool and seeing what the magnitude is. And if it's above a magnitude, in this case of 0.2, we know that there's going to be a void, a discontinuity. And then we move on to an equation here, an empirical equation, where we're looking at that same third harmonic over an average force, and we can, from this, predict the size of that void. So it's an area that we continue to work in. Another active area of research is friction stir welding aluminum to carbon fiber reinforced polymers, where the objective here is to, in these two images on the bottom, the white region on top is aluminum, 6061 T6. These gray circles are carbon fibers, and the mounting compound is the dark material on the bottom. And we're trying to get the aluminum to infiltrate into the fibers so the fibers become part of the aluminum versus just getting an interface bond there to strengthen that joint. It's a nascent area. We're just starting it, so I don't have many results to show except that you can infiltrate the carbon fiber with aluminum under a friction stir weld tool under the right conditions, but an active area of research. Switching now to metal cutting, we also do work in cryogenic machining. And here the objective is to cool the tool, hopefully without cooling the workpiece, in order to be able to increase tool life, or in some cases, increase speed. There are some machining operations that are temperature limited, such as with titanium. You can only machine it so fast before you run the risk of the part catching on fire. So you're severely limited in how fast you can machine that. If we can reduce the temperature in the cutting zone, which is the hottest temperature in a cutting operation, we should be able to increase the speed. So we've come up with a thermal model looking at different cooling strategies. The green line here is the internal cooling with liquid nitrogen, using two-phase flow to really remove as much heat and pull that temperature down. We've done a sensitivity analysis to figure out what parameters have the greatest influence on the outcome. That's nice, a good engineering model, but now the question is, how do we verify this? And that's why we're close to being there, but currently a student has been developing, or the process, right, to deposit thin film thermocouples on a commercial cutting tool. So nothing, not just a research, but a commercially available tungsten carbide cutting tool. Put down thin film thermocouples so we can measure temperature here, coat it, make sure the adhesion is enough to survive the severe temperature, pressure, shear, and abrasion that exists during metal cutting to monitor these temperatures. The last topic I'll just mention of active research is in additive subtractive manufacturing, where right now we've been looking at energy consumption in this and comparing the energy consumption if we use a wire-based deposition method, so think a gas metal arc welding torch, versus powder-based method. And sort of the general result is they're very similar in total energy consumption, which is not what our hypothesis was. We thought the powder-based would be much more energy intensive to make the powder, but that's not what we found. So with that, sort of an overview of a flavor of some of the manufacturing process research that's happening in the department and some national trends. Our next speakers will be talking, Justin will be talking about laser polishing. Sankey will be talking about manufacturing for design. That's not a typo. It's not design for manufacturing. He's working on manufacturing for design, to free up the designer, and introducing his lab. And Chris Smith will be talking about trends in robotics, specifically in the area of manufacturing, which is his area of expertise. So with that, I will gladly take any questions you might have. If there are no questions, then Justin?